Yeah, yeah, we are able to see, sir.
Yeah. Okay.
Yeah,
Yeah.
please.
Good afternoon to all of you. At the outset, I should thank the institution, Amalur Engineering College, for providing this nice opportunity of initiating SFA, Society for Failure Analysis, in Kottayam. This is the second one in Kerala, the first one being at Trivandrum. And I am also appreciations to the institution for having started metallurgy. I think there is the first one, although there are several metallurgists who have contributed in an evident way to various departments, including ours. I also appreciate Dr. Vishnu for following up with me in bringing out this chapter. And today, the birth of this chapter, the inauguration of this chapter has been seen so nicely. It is in coincidence. I should recollect that a very famous scientist who made the possibility of the existence of heavy hydrogen, that is the deuterium, and Ferdinand, who in the year 1930s worked with a lot of effort, experimentally proved that it is possible that deuterium isotope exists. Earlier, two of the seniors, they said that hydrogen contains deuterium possibility isotope. However, they could not prove. But it took some time, and it is this person, Ferdinand, who, by his experimental efforts, by compressing the hydrogen, making it liquid, and subsequently evaporating, made that deuterium is available. In fact, the seniors got Nobel in 1934, and Ferdinand celebrates his birthday. So it is like this, every effort to see an impossible thing possible require a lot of hard work. The institution has supported like anything. It has initiated metallurgy as a discipline in the first time in Kerala, and every one of you, faculties, students, 60 of you are around to see that SFA being initiated here in your place. I appreciate all of you for the efforts. Let me move into my presentation, about 31 slides. I would quickly go through them. And if anything you want to write to me, my email ID is param1961@gmail.com. Okay. As an outline, I thought I would introduce what is the title. It's microstructure, and subsequently what are the elements of that, how we are observing them in terms of either fractography or in terms of method. And there are three case studies, one with reference to manufacturing, one with reference to environmental, the other one is a simulation study. If time permits, I will cover all of them. I may be going quickly. I understand that the attendees are students. However, to try to grab and try to follow me, and if there are any doubts, you can raise or email me the questions. Why do we study the materials? We all know that material solids have a very stable form. For the time being, the other two states, liquid and gaseous state, let us forget. We know that solids are made of atoms, ions or molecules, which are sitting in well-defined fixed structure arrangement in the space. Therefore, we consider they are solid. However, they are not solid. They do fail. If you take glass, a cube of glass, and you take a cube of steel, drop them, steel will remain intact, glass will fail, into pieces. Why this happens? So there is something what you see with your eye cannot explain. This is the most important point. And there lies the structural arrangements which you talked, that they are well defined. There are something is there. This is because there are that are present in several dimensions in this material. It is right from 0 dimension, 1 dimensional, 2 dimensional, 3 dimensional defects present in the materials which you do not see with your eye is actually posing the trouble and making it fail. And this many of the engineers do not know, metallurgists will appreciate easily. And we all know that any material the designer suggests will be as a function of your that is synthesis. During surveys, there is change. I think metallurgists will appreciate easily. And the previous speaker spoke anisotropy again, which generates itself when you do a rolling or when you're doing an extrusion. These things are easy to understand for a metallurgist, but not to the mechanical production people. Therefore, they do appreciate, they have to appreciate the metallurgy of the materials to deal with them in an effective manner. So, what exactly is happening? I said that there is a structure, and that structure which is not visible to the eye. That means what? Something which is invisible means beyond our eye resolution. That is, a naked eye can see up to a resolution of 0.1 millimeter. That is under micron. So anything beneath this, you need see using a microscope. Okay. So a structure which is beneath this resolution, if you see under a microscope, you will be able to understand the materials and hence explain why the glass broke into pieces when you dropped it and steel did not. Okay. With this introduction, let me move. I already mentioned that defects can be classified as 0 dimension. What is an example? Point defects. Metallurgists should have read point defects are nothing but the vacancies in the lattice or or an interstitial atom present inside. If you take 1 dimension, all the metallurgists will immediately say dislocations, but mechanical engineers do not know. Then the planar defects, which are the grain boundaries. At length, Dr. Murthy spoke about casting and these grain structures develop, and when the grains develop from solidification, this solid will develop boundaries, and these are all planes, and therefore the planar boundaries are planar defects. Volumetric defects, I think it was just by both the speakers, previous speakers, Matthew told about inclusions, and you cannot melt a steel without inclusions. And cleanliness, a word used. I think metallurgists or the students of metallurgy surely can appreciate what is cleanliness. And it is partially, I think Dr. Murthy told, yes, the volumetric defects mainly are inclusions and of course void, porosity. These two also you should remember. I would also tell that those who work in our environment, nuclear environment, they appreciate a nano void, and for them it is very important because during irradiation, the material in a reactor get lot of point defects. They are basically lot of point defects are generated in form of vacancies and interstitials. These vacancies can come together to form what is called a void, and in the void there will be some gases that is again generated during the radiation, and therefore void swelling is a major problem for mechanical engineers in our center. They know void swelling, but they do not know or they have not seen the void. They have to see only through a microscope. So having said this, let us move further. Is the defects are limited only to this? No. All the mechanical engineers know forming, casting, welding generate defects. And they can see also easily with the help of non-destructive testing. That is the NDT. Also, there is a stress state changes. That is what residual stress. Again, previous speakers emphasized. Service defects. There's a changes in the dislocation structure. What is the dislocation? The one-dimensional defect structure changes when the material is put in service at high temperature in particular, and there will be segregation of elements, and which may results in new precipitation or formation of cavities, voids, etc. as a function of time in reactors. This is very considerable reason for many failures. Tell you that although the engineers design well, almost all the components are designed very well, they fail or they break. It is because there might be an applied load they anticipate. But as previous speakers also told, if there is a weld, there is a residual stress. The residual stress, I think Dr. Murthy mentioned as silent killer. Yes, silently it sits inside the component. It adds further stress to the applied stress, and therefore the material can give away. Or some service factors, corrosion factor, and the material can suffer stress corrosion cracking. Okay, and vibrations is another additional stresses. And of course, this is service environment. You look at some of the cracks which people ignore, the NDT people, even though they do an NDT scan of the weldments. You know, the weldments are critical places in a component, and these cracks will be lying very low, and engineers will say this can be allowed, permissible limit as per their design, but they will grow as a function of time and it will crack, as Dr. Matthew also has highlighted. Forming defects, I think hearing, all those things you would have read in the data book, so I am not going further into the detail. Let me tell you that as a function of time, that is evolution, local changes, microscopic changes in the composition can occur in high temperature service, particularly in an environment 500-600 degree, particularly in the components that serve in the reactors or in the steam generators, where diffusion changes will make changes in the microstructures, precipitations possible. Therefore, it will induce defects or the formation of a crack to extend further. So, undermine the importance of microstructure, which is the theme of my talk today. Okay, in addition, there will be some service related factors. Somebody might have using a switch in the wrong way can cause a component to fail. Okay, this for the time let me ignore. I have shown in the corner a bellow which has been mangled very severely. It is just because the switches, the DC motor that is running this bellow was connected in two different ways again and again, resulting in complete twisting of this bellow and it failed. Okay. Is the possibility of R&D from failure analysis? Yes. When there are premature failures, engineers will puzzle and get puzzled, and they will sometimes it is catastrophic, unsafe events occur, and therefore it is very serious. At that time, you need to understand a systematic study of microstructure and properties, and this is what is called structure property correlations. Is very important for our failure analysis. So, understanding properties in terms of what? Temperature, stress, radiation dose in the case of nuclear reactor. Temperature and stress, Dr. Matthew spoke at length about low cycle fatigue, creep. Okay, temperature alone means what? Thermal aging. If it is stress and temperature together, it is called creep. In the case of radiation dose, it generates large amount of defects. So, like as I mentioned, number of vacancies, number of interstitials are produced. So, precipitation, which you may not have thought about, which will, in a conventional way, will occur in our reactors. Going further, I would try to highlight that today in the talk, I would be touching about a few very small components. Most of the major components, let us assume, are designed very well. Minor components may have ignored. For example, a bellow, for example, tube fitting, or a manifold. Most of the reasons I think already listed at length by Dr. Murthy. I would put as reasons. as one choice of material, which is designer would have told, but however it is not available, or you want to have a cheaper material, you ignored and used another variety. Let us say 316, use 304. It's not correct. Then process induced defects. As I mentioned, during the process, there might be some defects introduced which people ignore. Unexpected seminar environment. Unexpected means vibrations can come or residual stress presence. These things will surely will affect. Corrosion can affect severely. Let me go into the next slide where you find that what is a failure. There are several definitions by the previous speakers, and this slide has also shown earlier. The main point here is failure means it is a cessation of linear elastic behavior. A material which is elastically behavior, that is deforming, it will come back. If it goes into plastic, then it will not come back. Therefore, failure means for a mechanical engineer, linear elastic behavior is very important. And this is the important thing for fracture mechanics. On the other hand, it need not deform, but it can break into pieces like brittle fracture. That is limited plastic flow. I think Dr. Matthew had given this. So this important definition you remember, the cessation of linear elastic behavior is defined as the failure for the mechanical. Let us go into in the failure analysis here today. I would be employing two things. What are the tools? I think there was a chat message. Two important tools, fractography and metallography. I would be using these two, and these two are the eyes for me to understand the failure. Let me go further. So what is fractography? How do you see that? You can see at a low magnification or simply with your eye on the surface of the fracture, or use a microscope. If the component is a very big component, like a turbine blade, go to the site, take a replica, plastic replica. This method you can learn, okay? And if you are able to associate with a laboratory, like Dr. Murthy's laboratory, or with Indira Gandhi Center, or with NAL or DMRL, for a month or so, you can easily study a case, and therefore replica method can be easily understood. Using a microscope, you will be able to see them, and you can section them at the backside of the fracture surface and see the metallography through optical and SEM. Therefore, the cross-sectional metallography will help. And people will think that why I'll talk about only microstructure. What is the implication on the property? The only important property for people like us is micro hardness. Although there are a variety of other properties, tensile, other things are there, you can measure micro hardness or the hardness. This hardness will give you an idea about toughness and also an idea about your strength. So very quickly you can get to know what are the properties around the vein region, what is the kind of microstructure. Is it the same from the distant area, or is it say, similar or different? So these things, once you establish, the cost can be understood. For example, I talked about defects. For example, this is a valve stump. On the left side, you have seen a stainless steel valve stump, highly deformed. What are the signatures? You can see there are different signatures. One interesting signature, the very parallel lines, suggests that this supports severe deformation twins, and slip bands are also there. They are interspersed along with this. So twinning as well as deformation by slip. Slip is very common for a stainless steel. But twinning is there means there is also high energy deformation has occurred. This is one suggestion which you get, and these are all two-dimensional debates that are all generated. If you look at a stainless steel which is deformed, you can see beautiful dislocation, one-dimensional dislocations. This is a transmission electron microscope picture. You see the dislocation is random, whereas in this band it is all arranged. So this is along this you find large amount of dislocations are there, and dislocation from here they can interact each other and they get confused state, and you will get what is called a debris of dislocations. And you see in this case on the right corner you find dislocations form what is called a cyclic thing. That this is a formation of dislocation when the energy, if they wanted to reduce the energy, they will try to form a network like this so that they can reduce themselves and they become stable. This is a case study which I studied in a low cycle fatigue sample where I could see the dislocations themselves rearranging into form of cycles. If you look at on the left side, a reactor component, stainless steel component, which has served very well. It has got exposed to irradiation. What is exposed into irradiation? It is basically getting generation of vacancies and interstitials. And the vacancies agglomerate over a period of time, and that is called evolution in the form of voids. And I can show you these voids, nano voids, can be seen only in TEM. And you see these white dots are basically voids, the white round ones. How do you say it is voids? A person who has worked in a transmission electron microscope know that the electrons travel through the sample. If it gets scattered, it will become dark. The image will become dark. If it passes through the sample, it will become white. So you could see the dislocation are getting scattered and they are going dark in the previous pictures. In this here, you find these round ones are basically voids, and these voids allow the light electrons to follow, and therefore the image form is white. And that is how you are able to distinguish them. You can count them, quantify them, and how this is varying as a function of several doses of. Dose is actually measured in terms of DPA, like you measure in terms of rupees, in terms of money, in terms of rupees. Okay, let me go into next one. This is a classic example of a grain boundary migration, which has happened in a creep exposed sample. What Dr. Matthew was speaking, this is a sample which has served for 30 years in the reactor environment. When it came to me for a steady failure analysis, I could see that number of precipitates around the grain boundary. You could see the triple point, several precipitates which are on fallen. Actually, the grain boundary has formed a migration here. So this is what is called grain boundary. This is due to creep. Okay. So all these things you can understand if you have a very good eye for microstructure. Now let me go through these case studies. Let us first have a case study by fractography, that is seeing only the fracture surface. I think people who spoke before me talked about ductile failure, brittle failure. What is the difference? Cup and cone, Dr. Matthew told, but brittle failure, shiny. You remember? The difference is it should be shiny. It will be, the light will be getting scattered and it will be flat. Okay. And in the case of what is so important, ductile failure, any example? For example, a turbine blade, if it extends a little, even by a fraction of an inch, it is sufficient that it will touch the surface of the dome. Therefore, ductile, that is, if the material, if it get elongated, there is a light limiting to the service. So therefore, turbine blades are designed for 1% strain or something like that. So this is how you should have certain important property. For example, in this case, ductility for the case of turbine blade. Okay, you have to specify. Let me go into the case study where you have given some samples. This was basically an extrusion. You see on the left side, region 1, region 2 I have given, and this was cold extruded or filtered rather. When it was driven through a die, and it came out into pieces like a crocodile mouth. And you see the pieces, and if you look very carefully with the naked eye itself, you could see some signatures are there. You see on the right corner down here, these lines are there. This a good fractography people will understand that this is basically a brittle failure. The shininess on the surface plus The line suggests it is not chevron or V type of pattern, means it has failed by brittle nature. As such, if you put it in the microscope, the fracture surface exhibit beautiful grains. I have not done anything to this, but you could see beautiful grains. And the grains are how they are elongated, oriented. Okay, that means what? It has suffered some deformation. And all the grains are flat. Certain grains exhibit a little bit slight differences, some small regions where something is there. In order to understand what is happening, you increase the magnification. And from 80x, I went to say around 300x in the next right side. You can see that certain grains are flat, but certain grains contain some amount of some deformation. That suggests that a little bit of deformation has occurred, plus grains are flat and caved away. So that means this is what is they have used a term called cleavage. Cleavage facets are seen. And Dr. Matthew mentioned inclusion. See the beautiful inclusion sitting here, the inclusion sitting here at the corner of the grains. They allow the material to give away like a pancake. You would have seen a pancake. So it will come out and it's a brittleness, very limited ductility. Okay, I also mentioned that fractography and cross-sectional metallography. Beneath you have two pictures. They exhibit the cross-sectional metallography. What is cross-section? Very close to the fracture surface. Slice it, polish it, etch it, like what you do it in your metallography laboratory, and etch it. You will see under the microscope beautiful grains, and the grains are decorated along the grain boundary with a lot of precipitation. What is that? I think Dr. Matthew or they mentioned that energy dispersive X-ray analysis in SCM. You can easily understand the chemistry, microchemistry specifically of the precipitates to find that it is rich in chromium and molybdenum. That means what? These precipitates are sitting there, and under this condition, if you deform or if you do cold filtering, it will only end up in the fracture of the tube, whatever you are trying to manufacture. So how to avoid this? You should make these precipitates go into solution. How to do this? Go to higher temperature and do a hot forming operation. Then you will be able to do a good extrusion or a filtering operation without a breakage. So this is the recommendation. And I would go into the second case study where metallography has helped to understand a failure of wire rope. Aerial wire rope is employed in our heavy water plant to transport coal from Singareni to Managuru. This is supposed to serve for 6 continuous years with a regular maintenance. Then the rope has been working nicely. But however, every month there is a breakage. So there is a consideration because the tons of coal that is being transported along this rope for a 9 kilometer across the highway is causing danger to the people who are traveling. Therefore, the serious concern was raised and the failed things were given to me or to our center, for example. The rope is basically 64 millimeter diameter and it consists of several rounds of fine round wires cross-section wise, and the last 2 outer sets are basically locked coil wire that is in the form of Z shape, so that they can lock each other and therefore they will be tight. But it is this Z wire, Z shape cross-section wire, which is actually failing. How it is failing? It comes out. When it comes out, the bucket which travels will get stopped, and after some time it tumbles down and it is danger. So therefore, we were given this failed piece. If you look at the cross section of the Z wire, it's basically a 0.7% steel. Means what? You know, 0.8% is 100% perlite. 0.7 means 0.8 minus 0.7 divided by 0.7. How much is about 1/7? 1/7 will be ferrite presence. So you find that it should be 1/7 is ferrite stringers with per light, other other things, or 6 by 7. But if you look at the edges, you find the structure is different. So the microstructurally, the probe exhibits on the outer edge, that is up to about 25 micron. I have shown the micron here, and you can see here the width measured. The structure is around 50-50, that is 50 ferrite, 50 perlite. That means it is 0.4% steel. But basically, this is heat treated, and instead of 0.7% here, the edges have got removed of its carbon. What is it called? Metallurgists will immediately say it is decarburization. If the decarburization is present, you will lose the carbon. Okay, if there is a carburizing environment, then it will become carburized. But this clearly shows it is decarburization has happened. Let it happen, mechanical engineers told me. Let it happen. What is so great about it? We have 64 millimeter, several wires are there, sir. Nothing will happen with this 20 micron of decarburization. In fact, decarb is permitted as per the American Wire Rope Association. So I have further continued. I showed the mechanical properties how it is. You can see clearly that a hardness map across the thickness clearly shows that the edges exhibit 200 VHM compared to the core, which is basically around 400 VHM. Correct? So that means what? The decarbonized air, as any metallurgist can appreciate, is basically a soft zone compared to the core. And is it good? But the American Association for Wire Rope accepts this, and we argue that it is not good for us. How? It's very simple. The buckets move. There are about 300 buckets, and a particular zone is decarbonized. That wire getting hit every 20 seconds. One bucket moves, and that 300 ton of load, when it sits, it gets deformed, and this deformed perlite, you know that it will get work hardened as a function of time, and we could see that the hardness of the edges will go high and it will become brittle and it breaks for a period of time. This is what we argued. Then they argued how it is possible. The wire gets decarbonized when it is heat treated during the manufacture. So what is the atmosphere in the furnace? The atmosphere is basically generated of propane gas, which when it is fired, it will convert into CO and CO2, whose proportion will determine whether it is carburizing or decarburizing. In fact, the decarburized surface has become hardened, and it has also given away, as I have shown in this microstructure, and therefore my argument is the fragmentation along the edges clearly shows that the decarbonized layer has been hit again and again by the 300 buckets every 20 seconds, leading to a deformed layer becoming very hardened, and hence it has lost its ductility. So decarbonization should not be permitted. So this is how I argued. In fact, that CO and CO2 combination, how it should be, is very nicely portrayed in good books of metallurgy. You can go through that, and whatever I have spoken, this is available in engineering failure analysis as a paper. Okay, for want of time, I will move further. The second one, where the solid interacts with liquid and gas, and this is why environment plays a part. In this case, in our case, so water, that is sodium, water, these are two are present, and this travel. And when they travels, water travels in the form of steam, and sodium is hot liquid. Okay, and how this interacts and what kind of failures occur. One is the caustic embrittlement. This is a form of the stress corrosion cracking. Several other corrosion methods like stress corrosion cracking, pitting, hydrogen embrittlement, all these things are possible in our environment. For example, steam, chlorine, hydrogen are possible. So I would try to touch upon two case studies and close. And the most critical component in our sodium systems. Liquid sodium system is the bellows. And the bellows, when they develop a small leak, then we have to shut down and we have to take out. And once it is leaked out, the material has been lost. Very difficult to understand how a leak has occurred. And we have to carefully see. And in this case, I have given a bellow. Bellow consists of two ply material and two sheets and folded construction. And I could see that it has given away and opened out for 3 millimeter or 2 millimeter hole, and one lip alone was there. And there are some interesting discussions. If you look at very carefully in detail, this around 1009 version, it shows some lines, beautiful set of lines, the fracture surface. The same thing further magnified, you could see beautiful striations in addition to a twin here. So that means what? There are some kind of an interaction which is exothermic in nature. All of you know by 12th standard that sodium, when it interacts with steel, it is exothermic. In fact, sodium is liquid by 90 degrees Celsius, and when steam interacts, sodium plus steam will generate huge amount of heat, and it can reach 800 degrees in no time. 800 degrees in no time. And this will generate or open out a very fine thin bellow material, and if there is a defect is present, it will open out, and through that, and that interaction causes Waller lines, which are basically these lines which are macroscopic. And in detail, if you look at it, you find that development of the twin bands along with a lot of striations suggests that there is also a fatigue effect caused by the interactions. Okay, what could be the reason why this has developed? Leakage wire it has been. So we try to see between the two plies through spectrography. The two plies with carrying the sodium debris here exhibits interesting microstructure. These sort of things are basically people working in stainless steel will know that this is for sensitization. Yeah? Anything? And the sensitization causes a material to get corroded easily. And how it is sensitized? Sensitization is basically a presence of more chromium going into the grain boundary, forming the chromium carbide, leading to depletion of chromium in the basic matters. And this results in attack of the grain boundary, and this is how this has happened. And are you sure that this is so? Yes. If you look at the cross-sectional metrography, it clearly shows this interaction result in grains exhibiting deformation bands which are interspersed with twin bands, suggesting the huge amount of reaction that has happened resulting in the failure. Let me go into similar thing, which is again a simulation work. With this I would close. Okay, there is our mechanical engineers wanted to understand this failure. They allowed the steam to pass through a tube, steam generator tube, and they provide a small hole in the steam generator tube, and they close that hole with a stainless steel rupture disc. Rupture disc means its thickness is very less, about 50 microns or so, and they scribed on the outer side with the plus mark as shown here in the right side. And they expect that when the steam is passed inside and pressurized, this will open out as a petal and interact with the sodium which is flowing in the outer tube here. And unfortunately, this rupture disc failed not like a petal but as a linear crack. So they wondered why it has cracked along a line. So they wanted to know the reason, and we have examined it in detail. In the next few slides, I will close and I will tell you what has been the reason why a linear crack has emerged. With that, I will close. The starting material is very simple, 10 to 12 micron grain size, very good austenitic stainless steel. No signatures of deformation or nurses 220 VHN, a typical microstructure of an arsenic stainless steel. Grains are very fine prior to testing. Mechanical rupture test is subject to mechanical things, everything has been done. If the piece which was given to me after the testing was done, on two sides we have examined. Inner surface exhibit linear crack. Outer side you could see the plus mark, and you could see debris thrown out, white debris on either side, 70 micron, the long crack, debris thrown around up to 500 to 600 micron, and we examined the microstructure in detail of these two discs, this disc on either side. We could see what could be the microstructure evolution as a function of this exposure to the possible reaction of sodium and steam. If you look at the edge before contained debris of sodium oxide, and there is also the edge exhibiting incipient melting condition, and the distance around 250 micron, lot of decorations of the grain boundaries. And of course, here if you look at it, the grains which I have not etched it, as such the heat has etched it, having good amount of micro cracks. So these are all the information. Now in order to understand why such bands are formed, we try to understand that the SCM level, you could see something like this, and bands are there. Whether these are all simple deformation bands or is it due to twinning? We know that already that it is possibly high temperature, high pressure, both might have happened. So whether deformation bands are due to twinning also, a detailed electron microscopy is done. So you could see the parallel bamboo-like twin bands beautifully seen at the edges. This is the edge. You could see that deformation bands are nothing but twinning bands. So that means the twin has dominated extensively in this because of the high temperature and pressure generated by sodium steam interaction. We look at on the right side as well as beneath the debris of dislocation. The kind of dislocation which I showed earlier as example are quite different than this debris. This debris is very severely interlocked, and therefore the dense dislocation formation, this debris formation suggests that the reaction rate, the deformation rate is very fast. Okay. So with this, I will try to conclude saying that microstructure is very important, and what you do not see with your eyes can be seen through the microstructure. With the help of microstructure, a fracture surface study will reveal certain details. The cross-sectional metallography will reveal certain microstructure evolution in terms of the precipitation, in terms of the dislocation structure, in terms of the bands, deformation bands, etc. I had provided 3 case studies. One is the monthly recurring failure of wire rope, and I showed how decarbonization is the cause. I also showed HIZ, sensitization of the material, which can cause a failure, and failure simulation done by our mechanical engineers, why the failure has been, the crack has been as a linear crack. So microstructure can give easily an answer to the failures, and in these few words, I also appreciate the efforts of Kottayam chapter in making SFA opened out there. I wish all the very best to all of you, and many more continued interactions, and please do share your views, and newsletter is one where you can always write an article. Please do that. With this, I wind up. Thank you very much.